Hello, everyone. Welcome to the next instance of QSI seminar. Today, we have an honor to have Kunal Sharma from University of Maryland to give us a talk. And Kunal will be talking about the trainability of parameterized quantum circuits. So thank you very much, Kunal, for joining us, and take it from here.
Thank you, Maria. Thank you for the invitation, and thanks everyone for joining. So yeah, I mean, in this seminar, I'll try to put most of the results, at least where I was part of, like projects where I was part of, under one umbrella, and also mention other results at the end of my talk. So this is the grand goal of quantum computing. Maybe in some years or maybe in some decades, we'll be able to do these applications effectively if we have a fault-tolerant device. But until then, we are limited by number of qubits. We have limited connectivity because of a given hardware. And then we also have some limited coherence time for a given qubit. And then you apply gates on them, they are noisy. And then we have either coherent noise where, let's say, you try to do some rotation and then you do that rotation plus some error, or you have incoherent noise in terms of, let's say, depolarizing noise or Pauli noise or other kinds of noise. And because of these reasons, we are limited by circuit depth. So we cannot do these algorithms, which we have been working on in the past 20 years. And then you can ask this question, what can be done with these near-term devices? And now we have a term for that, which is called NISQ devices, noisy intermediate scale quantum devices. And different companies and different academic groups are going for like increasing number of qubits, improving the gate error rates and other things. And I've just put an example of IBM where, I mean, if you look at this timeline, the goal is to go for, let's say, millions of qubits in a decade or so. And so, I mean, we have 10 years or maybe 20 years, and you can ask these questions now, okay, even if we have thousands of qubits, can we do something useful? And in my opinion, you can maybe think about two different things which you can do with these devices. First is quantum simulators. So since these are not universal quantum devices, because they are not fault-tolerant devices, we can think of them as simulators. But maybe simulators with more control than previous physics experiments we did. So we can use these devices to do more physics experiments better than what we have done so far. Another thing which we can do is variational quantum algorithms. So I will define the framework in the next couple of slides, but we essentially have been doing these algorithms on classical computers. So for example, if I want to solve some physics problem, we try to define an optimization problem corresponding to that physics problem, and then use classical computers to solve them to get approximate solutions. But now we are hoping to use quantum devices to do at least some subroutine of that whole algorithm and get some advantage over classical devices. So there are several algorithms introduced for different problems. And there are review papers already in this area, and I'll recommend to look at these review papers. If I explain variational quantum algorithms or even the quantum machine learning setup, then this slide is the most useful slide. For a given problem, you define a cost function. Let's say for energy minimization for a given Hamiltonian, you can define the cost function in terms of expectation value of some, let's say, Pauli string or some other observable. So the way variational algorithms work is that you start with some state, rho, and then you apply a parameterized quantum circuit. I'll define it more carefully, but you can imagine that you apply some single qubit gates, 2 qubit gates, and those single qubit gates are like angle dependent, which you can tune. After preparing some state here, you do the measurement, calculate the cost function, and then feed that information to a classical computer, which does some optimization. The most famous one is, let's say, gradient descent algorithm. Through that, you find new set of parameters, and then you feed that information again to a quantum computer. And the goal is to now use those new set of parameters on your initial state rho and get new cost value. And then you continue this loop until you reach to your desired solution, and according to your definition of precision or number of steps, and there are many variables in this. There are several problems, or there could be several problems in this whole setting, but I'll just hint at three major issues. One is the noise. As I was explaining, that even state preparation has noise, gates have noise. So whatever you do in this whole framework, you will be bounded by the noise and you will have accuracy issues. Another major challenge is how do you estimate the cost value efficiently? And there have been many excellent results in the last maybe 6-7 years where, I mean, recent one is this shadow tomography, where, I mean, at least now we have a solid way to do these measurements efficiently for a given problem. And then the third one is the trainability. So even though you could do these parts, let's say properly, let's say you could fight against noise somehow and then do this efficiently, we have to make sure that the cost landscape through this framework, whatever cost landscape we get, it should be trainable such so that we reach to some good local minima or even global minima if possible. So in my talk, I'll be focusing on this trainability part. As I said, parameterized quantum circuit, you can think of it as a unitary, which is parameterized by some angles. And you can even further break in terms of these, let's say, L different layers of unitaries. And I have like simplified a picture here because I'm just saying, okay, in this unitary, there is just one angle, but here this one angle could also be like just a vector of angles. So you can look inside this unitary again, and you will see that, okay, I have parameterized it using single qubit unitaries and 2 qubit gates. And now these angles could be variable. And depending on the problem, let's say if you're trying to solve some chemistry problem or some optimization problem, you can have a specific structure to this onsets or parameterized quantum circuit. Or if I'm trying to solve some machine learning problem, let's say if I'm solving some, if I'm trying to learn a function, learn a unitary connecting input and output states, where I don't have much information about the problem, then I could keep these gates completely random. So again, depending on the problem, you can divide it into two different categories. One is problem-inspired onsets. As I was explaining, this is a well-known onsets for chemistry problems when you're trying to find, let's say, ground state energy of molecules, molecular Hamiltonians. QAOA is a well-known onsets for solving combinatorial optimization problems. Hamiltonian variational ansatz is another ansatz which is sort of inspired from QAOA, and I'll speak about it in detail later. So here in these ansatz, we use the information about the Hamiltonian we want to minimize the expectation value of, and that's why maybe we can reach to solutions easily, at least in these problems. But then, as I was saying, for some machine learning problem, we don't have any clue about the problem as such. And that's why these hardware efficient ansatz are defined, where you just apply, let's say, a block of single qubit and 2 qubit gates, and then you just apply them randomly. Even in this, there are two different kinds of ansatz. One is fixed structure, where you, let's say, you want to apply a layer of these single qubit and 2 qubit gates, and then just you repeat the same structure. And then another kind is variable structure ansatz, where maybe you apply this, let's say, structure ansatz, but then randomly remove gates or add gates. And it has been shown that, I think, for problems where we don't have any way to create good ansatz, maybe variable ansatz is a good way to go ahead. And there was a recent paper on this showing that variable ansatzes are better than the fixed structure ansatzes. And on the neural network side as well, there are different ansatz, and one of my favorites is this quantum convolutional neural networks because they are of log n depth, and maybe you can use them for classification tasks. Another key component is the cost function, and these are the properties which it should satisfy, that it should be faithful. Once you reach to the minima, it should correspond to your desired answer. Another key property is that it should be efficiently computable, because if it is not, I mean, or at least it should be computable on quantum computer, but not easily computable on a classical computer. And that's the way we sort of argue that, yeah, maybe these algorithms can do better than classical computers. And then trainable is another key component. So mathematically, you can just define them. Let's say for simplicity, you have different states. So I'm trying to encapture both variational algorithms and also QML setting here, where you have a state, you apply your ansatz and then do some measurement. And then you can also do some post-processing on it. And depending on, let's say, in a QML setting where you have, let's say, training pairs, and that's why you have different K initial state and corresponding observable. So in my talk, I will first actually explain two major results, like first results on trainability of parameterized quantum circuits, and then mention our result where we try to connect the expressibility and trainability. And then I'll discuss the perceptron-based quantum neural networks and their trainability. And then I'll talk about like problem-inspired answers, and finally, what happens when you run all this in the presence of noise. So going back to the same picture, you start with a state, apply an ansatz. Mathematically, you can represent them in terms of these unitaries. And now let's just focus on this simple cost function, which is just some Hamiltonian expectation value. Now, let's just look at some parameter theta I in this circuit. And you can ask this question, what happens when I try to find the variance of the derivative of the cost function? And it was actually studied in this paper by Jared McLean and co-authors. And what they found was, if your circuit is sufficiently random, so let's say if I have an n-qubit circuit and this whole n-qubit circuit is sufficiently random, or if this whole n-qubit circuit is to design, and I'll define that in next couple of slides. When the n-qubit circuit is sufficiently random, then the variance of the derivative with respect to any parameter you take in your circuit actually gets exponentially suppressed in the number of qubits. I mean, the mathematical expression was like this, where even if you assume that these quantities, trace of h square and trace of vi square, scale as d, you still have 1 over d in the variance. And if you use Chebyshev inequality, then you can argue that probability of finding a finite variant with respect to any parameter in your circuit is exponentially suppressed. So that's like the negative side of starting with a random or choosing a random circuit for these variation algorithms. And this is the well-known Barron plateau phenomena. And they also study it numerically, because you can argue that whether I hit to design or not, what will happen. So they studied it for a simple case where they start with all zero state, apply a fixed rotation, and then apply rotation about x, y, or z axis randomly. And at the end of the day, they do a measurement on the first 2 qubit sigma z measurements. And here they are plotting the variance with the first parameter in the circuit against the number of qubits. And here you can see that it's plotted on a semi-log plot, and you get a straight line, which means variance is exponentially suppressed in number of qubits. So main message, I mean, on this slide is that if your circuit on n qubits is to design or highly expressive, then you have this Barron plateau phenomena. And after this paper, in this paper by Cerezo and co-authors, they asked this question that instead of looking at whole circuit on n qubits and saying that this is sufficiently random, let's just look at the blocks of circuit. And this is sort of the regime of hardware efficient ansatz. So if I just imagine that I have these k qubit blocks and I'm applying on these neighboring qubits, and now you make an assumption that these blocks are sufficiently random, or these blocks are forming 2 design on k qubits, then what they found that the Barron plateau phenomena was cost function dependent. So if I choose a cost function where I'm measuring all qubits, let's say sigma 1 to sigma n, any Pauli, or if I'm doing a Hamiltonian expectation where I'm just doing some local measurement, then you find different kind of Barron plateau, which means in the global cost function case, you have Barron plateau everywhere. It does not depend on the depth. Or on the other hand, for local cost function, if your depth is order log n, then it is trainable. In other words, what they do is they try to find a lower bound on the variance, and they show that the lower bound is not exponentially suppressed. It's like 1 over poly in number of qubits. On the other hand, if you go to poly n depth, then you again have Barron plateau for local cost function. So I would say that this poly n depth regime is actually what previous papers studied, because they were saying that you have to design on n qubit circuit, and the new result in this paper was up to this log n depth circuit. So, I mean, after looking at these two papers, you can ask this question: what is it which is making these circuits untrainable? And that's something we study. We try to find the connection or mathematical relation between expressiveness of a circuit and the trainability of a circuit. So before talking about the mathematical structure of it, let's just look at this simple example. So whenever you define an ansatz, you define it through set of unitaries, how you arrange them in a circuit, and through these parameters. So suppose in a given algorithm, you will only do some finite number of angles, like you will tune those angles and then only generate finite number of those. That means you will create only a finite number of unitaries or an ensemble of unitaries. And imagine that your ensemble is such that it's exploring this blue shaded region. If your ansatz is not expressible enough, and here by expressiveness, I mean that if you're not, or how uniformly you are exploring the unitary space. So if it is not expressive enough, maybe it can find solution to some problem A, but not some other problem B. But if your ansatz is expressive enough where you are exploring uniformly, then you will be able to solve two problems using the same ansatz. The idea here is, I think all this I'm talking about those problems where I have no information about the problem, let's say in the QML setting. And there I would prefer exploring it uniformly. So what we find in this paper is that if you go for uniform exploration, so even if you don't hit to design, even if it's approximate, you will still have these vanishing gradient issues. On the other hand, if you try to explore it on a subspace, it does not guarantee for sure that you will not have variant plateaus. What we find is that you can have both of these situations, and I'll explain that in our numerics through our numerics. So let me just define this mathematically as well. Just to reiterate that, let's say you create this ensemble, and now you can define this super operator where on one hand this is a unitary, or this is an ensemble where you are trying to sample them uniformly, like according to the Haar measure. But here, this is the ensemble you are creating through your variational circuit. And through this super operator, I mean, this is essentially what a T design is. Through this operator, you can now define these two quantities. And these two quantities are sort of like expressibility measures, which we considered. It was actually defined in previous papers, but we try to connect it with the variance of the derivative. So what we essentially find, so I mean, the details are not important, but just to reiterate that this is the ensemble you are creating on your circuits, and this is like the most expressive circuit where you are like sampling unitaries with respect to Haar measure. So the main result is this upper bound on the variance of the derivative. So let's say with some parameter k, you calculate the derivative and then again find the variance. The first term doesn't really matter here because it's exponentially suppressed. And the second term is depending on this expressibility measures. So since first term is anyway exponentially suppressed, you can see that if your circuit is highly expressible, which means these epsilon values are super small, then you will have small variance. So the main message is, I mean, this result is sort of suggesting that even if you have approximate two design, which is like sort of intuitive, but we were just putting this in mathematical framework that if you have approximate two design, depending on the epsilon values, you can still have like small variances. And obviously we don't have a lower bound, so we cannot say anything about if it is not expressive, can you still have variant plateau issues or not? So I'll try to explain that through numerics. So I hope you could see the connection between the mathematical form I showed and then these pictures. So for numerics, we again consider a similar problem, which McLean and co-authors did, where we start with, let's say, all zero state, and then we apply rotation, fixed rotation about y. And then we define this ansatz by these rotations where the axis is chosen uniformly between x, y, or z. And then after applying these rotations, you apply, like it's 1D connectivity, you just connect neighboring qubits with control z. So you can ask this question, okay, what if I just restrict my rotation direction? So as I was saying that you pick rotation directions uniformly between X, Y, or Z. What if I just pick just X? I mean, in each rotations, I just don't do this randomness. And at the end of the day, maybe you can measure a global cost function where, let's say, it's all poly operators on all qubits, or you can just measure, let's say, poly operator on first two qubits. So what we find is the following. So forget about first two columns. Let's just look at the last column. The first box is for global cost function where you measure all qubits. And here, irrespective of the rotation direction, whether it's just Y or just X or between X, Y, or Z, what we find is that you will always have variant plateaus. So it is sort of resonating what Cerezo and co-authors did. And in the case of local cost function, where let's say we just measure first two qubits, here if you are allowing all possible directions in those rotations, this red line, then you have variant plateau issues. But if you fix your rotation directions, let's say X or Y, then you actually get rid of the variant plateau issues. So this was sort of a positive side in a way that if you try to remove the expressiveness, obviously it's problem dependent. I mean, we are studying specific case where I think we are measuring sigma Z at the end of the day on first two qubits, and the ansatz is, let's say, defined in terms of rotation about X or Y. So, I mean, for at least for this specific problem, if you restrict your rotation directions or try to decrease the expressiveness, then it can avoid band plateaus. So, I mean, but I think what is missing is like the framework. Like, how do we argue about losing expressiveness leads to trainability? I think that framework is missing, and it's also challenging to define that framework because, as I said here, that even though the circuit is losing expressiveness, but since the cost function was global, you still find these band plateaus. So, I mean, if there are any questions, I'll be happy to answer. But so far, whatever I discussed the parameterized circuits where you start with some number of qubits, apply gates, and then do the measurements. But I did not consider a situation where I discard qubits in my parameterized circuit. And I think there was sort of a speculation around, let's say, last year, a summer, or even before that maybe if you start discarding qubits in your circuit, maybe it can avoid these band plateau issues. And actually, it was hinted in this paper by Beer et al. And I'll explain their setting. What they were arguing that if you discard qubits in your circuit, then you will not have these band plateau issues even for deep circuits. And that was like very fascinating to read about, but we studied it carefully, and I'll describe those results now. But the setting is as follows. It's sort of similar to how you define a classical neural network, where you have neurons in your input layer, and then you connect it with the next layer through some nonlinear function, and then you continue that and reach to the last layer. Here they replace these nodes with qubits, and then they connect these qubits with the next layer through unitaries. So the perceptrons are now unitaries. Just to clarify further, so let's say in this example, I have 3 qubits in my input layer. I'll connect these 3 qubits with the first qubit in the next layer, and then I'll connect these 3 qubits with the second qubit, and I'll make these connections. And after all the connections are made, I'll just discard all these 3 qubits in the first layer, and then I'll try to make these connections from second to third, and again discard my second layer. And I think so they did some numerical analysis, but it was done on a small number of qubits. And the argument they gave was because we are discarding qubits, they sort of expected or hoped that it avoids band plateau. But what I'm going to argue now, that it does not happen if you have deep circuits when you are making these connections. So whatever I spoke here about these connections, you can define it mathematically here, where you start with, let's say, some input state, and all these qubits in the hidden layer and also in the output layer, you start in 0. And then you apply your onsets, which means these connection unitaries. I mean, there's this toy example here, which I explained. And at the end of the day, you are getting rid of all input qubits and all hidden qubits. And they pose this as a QML setting. So where you have input output pairs, and let's say there are n of them, and your goal through these dissipative quantum neural networks is to learn this target unitary, which is connecting input state to output states. Or in the classical setting, it's like learning a function. So you can define a cost function here as well in the QML setting. And it's essentially the overlap. So you can define overlap between the true output state and the output state you generate through this parameterized circuit. And for special cases, so you can see here that this is a global cost function. But for special cases where the output state is a product state, then you can also define a local cost function. So I think I should have emphasized this earlier, that when this global and local cost function dependent band plateaus were introduced, I think everyone started thinking that, okay, we should always define a local cost function. But when it comes to these QML tasks, it is not always possible to define local cost functions. Only like specific settings where it is tensor product, then only you can define it. Otherwise, it will be an approximate local cost function. The perceptrons I discussed earlier, there could be like different kind of perceptrons, but I'll just focus on this first kind. So where you are connecting all input qubits to one output qubit, but you can also define, let's say you just connect few qubits from your first layer to one qubit in the next layer. So results are sort of again discouraging, because if you imagine that these connections, if these unitaries, so let's say you start with n qubits and connect with 1 qubit. So this is an n plus 1 qubit unitary. So if this qubit is sufficiently random, again, if I imagine that this is forming a 2 design, then you still have the same band plateau issues, which means irrespective of whether it's global or local when it is a tensor product state, the output states, irrespective of global or local cost functions, you still get this upper bound on variance, which is exponentially suppressed in the number of qubits. So this was sort of like contrary to what Beer et al. Were proposing, that discarding qubits can help. So I will emphasize that our results are sort of suggesting or like indicating these entanglement induced band plateaus studied by Maria and co-authors, where the argument is that if you have a circuit where, let's say, you apply sufficiently random unitary on, let's say, n qubits, and you can also say that sufficiently entangling unitary, and if you discard now some qubits from it, then whatever is left over is sort of like maximum mixed state, and you should not be able to train your parameterized circuit. So this is sort of like hinting at entanglement-induced band plateaus as well. So this is the summary so far. I mean, I connected the expressibility with the trainability, and I think it would be good if we have a framework, because that would help in designing onsets, whether you can really make things trainable by sacrificing expressiveness. And we also had some positive results for these dissipative quantum neural networks, where we tried to represent them as hardware efficient onsets, and then directly use results of Cerezo et al. And argued that, okay, even in QNNs, you can have a situation where when they are trainable, but I think there are more results required when you define local perceptrons. So I think there could be a hope that using dissipative circuits with local perceptrons could actually avoid band plateaus, but I think no one has studied them so far. So all the results I presented so far did not use any information about the problems. So you can ask this question now: if I use problem-inspired onsets, can I avoid band plateaus? And I will focus on specific kind of problem-inspired onsets, but I should emphasize here that no one has studied, or at least mathematically argued, that whether these chemistry onsets, unitary coupled cluster, avoid band plateaus or not. So I think that's something still, I think maybe people are studying, but it would be great to like show it rigorously. Another thing which I have not discussed so far is what happens when there is noise. So are there any questions? I think I don't see anything in chat, but I'd be happy to take questions if there are any.
Yeah, so I have a question. So, is there a similar result in the training of classical neural networks where you have to choose between trainability or expressivity, or is there something uniquely quantum about to design that gives rise to this either or result?
I think that's a good question. Yeah, I'm not sure if they try to, I mean, there are results in classical setting, but I think I am aware that in the classical setting, there are results similar to band plateaus, but I think they talk in terms of depth of the circuit. But yeah, I think it is matching with this expressibility. Yeah, so I'm not too sure about that.
Mm-hmm. And
Yeah.
also, when you are talking about training, yeah, I read your paper a while ago, but I don't remember all the details. When you are looking at the objective function, is it always of the type that you are measuring some observable in a state?
Yeah, that's correct. Yeah, it's always in terms of observable. Yes.
Okay, thanks.
Mm-hmm. Yeah, so I think I'll mention about your recent result about using these Rennie divergence. I think that's a neat idea, and maybe we need more results of that kind, changing the cost function. Okay, so now I'll discuss these problem-inspired ansatses, which are of special kind, which means it does not capture all possible ansatses, but at least these two. So here what I'm doing is I'm defining these L different layers, but when I define like one layer, like the first layer, which is defined in terms of, let's say, these unitaries, when I go to the second layer, I use the same Hamiltonians, same unitaries, but with just different angles. And that's sort of like the structure of QOA or Hamilton variational ansatz. And mathematically, they are defined like this. So QOA is very famous because it was proposed to solve this combinatorial optimization problem. So let's say you want to find, you want to minimize a problem Hamiltonian. You use this unitary corresponding to problem Hamiltonian, and then you use a mixer unitary, and then you just repeat these two unitaries in terms of P layers. And the hope is that I think this QA ansatz is backed by adiabatic theorem that if you have large P, then you will definitely reach to the correct solution. But on the other hand, I think inspired by this QA ansatz, this Hamiltonian variational ansatz was defined in this paper, where what they said was, let's say you want to find ground state of H, and H is given in terms of non-committing terms, HS. Then like here we had problem Hamiltonian, mixer Hamiltonian. Here they just argue that, okay, just use the terms of HS, like first order totalization, and then just repeat it. So, I mean, at least QA had this backing through adiabatic theorem. I don't think HPA has any rigorous analysis why this kind of setting should work for large P. So I think that's something as well. I mean, should be studied in my opinion, because numerically people have found that these kind of ansatses also work even for like finite values of P. So our goal was to find a mathematical reasoning why these kind of ansatses can avoid barren plateaus. So the story was when we finished our projects related to dissipative quantum neural networks, we started thinking about, okay, does QOA have barren plateaus or not? And numerically, we found that at least the max cut problem, which we all solve all the time, that ansatz does not have barren plateaus. And we were very curious, what is the reasoning behind it? Can we connect the variance of the gradient with some other quantity? And that's what I'm going to talk about now. And for presenting that, I have to introduce this background on this quantum optimal control, because that's how we argue, or that's how we make connections with the variance of the gradient. So this is, in this case, what we really do is we look at the Hamiltonian. We just go one level down. Instead of looking at unitary, you just look at the generators of those unitaries. So let's say this H0 is your parent Hamiltonian, but then you have these pulses which are tunable. And then if you change those, then you effectively change the unitaries. So they are essentially like two sides of the same coin, which is shown in this picture. Like here I have these circuits which are defined in terms of these layers. And if I look inside, then I have these different pulses which I'm tuning. So once we are in this framework, now we can talk about what are the generators of my what are the generators in my onsets. So by generators, I mean all the Hamiltonians I'm tuning in my onsets or parameterized quantum circuits. And then we can talk about the Lie algebra formed by these generators, which means you have these generators, you find commutators between them, you get new elements, and then you again find commutators with the new element with the previous elements, and then generate the whole Lie algebra spanned by these generators. And then you can define a Lie group, which is just the exponentiation of the generators. Now, I mean, there is different categories of these Lie algebra. I mean, I think I'll not go through those, but essentially, depending on the rank of these Lie algebras, you can define these different categories. So if you, let's say, if your algebra is a full rank, which means you can create all possible unitaries, then it's called controllable. And if you cannot, then it's called uncontrollable. And then you can define subcases of those where, let's say, even though you cannot explore the whole Lie algebra, but on the reduced or on the sub algebra, you can have, let's say, your algebra as a direct sum. And then there itself, you can talk about controllability. So, I mean, the main message here is that depending on what are your generators, you can talk about the unitaries you're going to explore in the unitary space. And there are different categories of those. But our results are sort of dependent on this. So, I mean, I'll just leave it for a second and I'll come back to this. So these are our results. So we were just trying to connect back to what results we already know, and which means connecting back to two designs, because that's how all previous results were shown. So let's just look at this example where the hardware efficient ansatz, which I discussed earlier, the usually hardware efficient ansatz is defined using single qubit rotations, let's say about X or Y, and these 2-qubit gates connecting neighboring qubits. So I'm again thinking in terms of 1D connectivity. So these are my generators now for hardware efficient ansatz. And then using this, so you can define an algorithm for finding like the whole set spanned by these generators. So what you find is that these generators actually cover the whole Lie algebra, and that's why this kind of ansatz will hit a two design eventually, and they should have barren plateaus. So this was an argument for barren plateaus connecting with the dimension of the Lie algebra for hardware efficient ansatz. We also talk about spin class ansatz, where these are the generators, and even for this ansatz, you can argue that these generators again cover the whole Lie algebra, and that's why they should have barren plateaus. But now, can we argue using this dimension of Lie algebra? Can we argue that you can avoid barren plateaus? So that was the next question we try to ask. So this is an example which I'm giving. So transverse field Ising model, I mean, these are the generators for that. You can also think about them, I think, as your max cut problem, because these are your problem Hamiltonian and this is your mixer. In this case, if you try to calculate the dimension of Lie algebra, then it turns out that it is actually polynomial in the number of qubits. But now let's say if I add another generator in this whole Hamiltonian. So I have these two generators, but now I also introduce these longitudinal field, these ZIs. Now the dimension of Lie algebra actually goes from polynomial to exponential. And in the next slide, I will show that, and at least numerically, what we show is that this is trainable, which means there is no barren plateaus for this ansatz. But as soon as you add it, like this simple change you made, where you added a new field in your ansatz or you added a new generator in your Hamiltonian, then you again have these barren plateau issues. So I think the main message is that when we are designing these ansatzes for the problem-inspired Hamiltonians as well, we cannot, because there were results where people are suggesting, okay, let's just bring new mixers. Why do we just focus on one mixer? Why can we not have multiple mixers? Or why don't we randomly bring new mixers and adaptively change the cost function. So our results are suggesting that if you bring a new mixer, it is not necessary that you will avoid barren plateaus. You can even hit barren plateaus. So this is our numerics. So forget about these close and open thing. By close, we mean that we connect the first qubit with the last qubit, and open, we mean that we don't connect them. So let's just focus on the open case. Here, this is a transfer field Ising model where you just have ZZ term and the X term. And this is a longitudinal transfer field Ising model where you also introduce these Z terms. And here I'm just explaining these ansatses on 4 qubits. So you start with the ZZ term, apply X, and here along with X, you apply Z. And just to emphasize that you have like same angle everywhere, because this is the feature of like these problem-inspired ansatses. So there was also this these results saying that, oh, maybe correlation between parameters in your circuit can help avoiding barren plateaus. So that also we had as a question. And I think there is one paper which directly studies correlation, but in these problem-inspired ansatses, at least in the QA setting or HVA setting, there is correlation between different parameters. So this is our main result. What we find is that when you let's just look in the open case. When, let's say, when we just studied the transfer field Ising model, you have this variance which is not exponentially suppressed. On the other hand, when you do the longitudinal transfer field Ising model, which is like the green triangles, you see that the variance is going exponentially down. And again, it's on the semi-log plot. That's why it's a straight line. And this is this curve. And I think the main message of our paper was, this is our observation, we did not prove it, was that the variance of the gradient actually goes as 1 over poly dimension of the Lie algebra. And this is what we are plotting here. So here again, variance is plotted against this 1 over dimension of the Lie algebra. And this plot is showing that it goes as 1 over poly of dimension of Lie algebra. And this is still sort of, we cannot prove it, and we just studied it numerically. But for different cases, which I was presenting here, like for all these different cases, what we found numerically, that this result was holding. So, I mean, in principle, it gives a way, even though we did not prove it, like we numerically observed it, in principle, it gives a way to create ansatses where you can, let's say, find out what is the dimension of the algebra, and then you can guess whether your problem-inspired ansatz will avoid barren plateau or will have barren plateaus. I should emphasize that at least for some cases, we had like analytical results, but not for all those different subcases of the dynamical Lie algebra. So these are the main message, that we developed this framework to study periodic structure ansatz, but it does not cover, again, UCC. So it would be great if there are results on UCC. And maybe our framework is now providing a framework to do these adaptive ansatzes where you can bring new mixers, but make sure that you don't have dynamical Lie algebra going exponentially in number of qubits. And this is our observation, and it would be great to prove that it depends on the dimension of Lie algebra. So now I'll move to the final section of my talk, and I think take maybe five minutes or 10 minutes maybe, where what happens if you add noise. And this part, I think this part of my talk is quite obvious, because we all know that as soon as you start adding noise, everything should just go bad, because noise will take over all the patterns of behavior you brought through your parameterized circuit. So the setting we considered was, I mean, it's similar to what I've been discussing so far. Start with a state. You had these unitaries, but now before and after these unitaries, you have these noisy gates. So in our paper, we considered a setting where we apply single qubit Pauli operators or single qubit Pauli noise. I think our results also hold if you apply, let's say, k qubit Pauli noise. So now you can ask this question: what will happen to my gradient when I have these noise, and up to what depth can I go? And I mean, as I said, that noise should take over and everything should just become flat, and that's what we observe. This is just to explain Pauli noise. It's just like shrinking the block sphere. And what we find is the following. So I think this is confusing. What is LM? But just imagine that in your same ansatz where you have these different unitaries up to L layers, you just pick one parameter and try to find gradient. What we show is that the magnitude of the gradient is upper bounded by this function where Q is the noise parameter. Yeah, I should clarify that even though Pauli noise has different parameters, we parameterize it such that you just focus on single parameter to get this neat result. So what we find is that the upper bound is actually a function of this Q, which is the Q is less than 1. The modulus of Q is less than 1. And it goes as Q to the L, which means if you go to linear depth circuits, so linear in number of qubits, then you again have these vanishing gradient issues, but now because of noise. And I should make these distinctions that here I'm not doing any sort of averaging because I'm just looking at gradient with respect to some parameter, and I'm not looking at the variance. So I'm not doing any sort of averaging. So this randomness effect is not going on here. It's essentially just saying that, okay, noise is just making everything flat. So this is sort of discouraging because if you look at the problems which we hope to like use and get some advantage over classical methods, let's say QA or chemistry problems, I mean, all those ansatz required at least linear depth circuit. And I mean, at least I mean, there are two kind of costs. One is where you compile your unitary, let's say for QA, compile that unitary, and also like go to larger value of P, like P is the different rounds of QA. So there are two different ways to increase your depth. And I mean, there are papers studying saying that P has to grow with N, and the compilation also for at least for 1D circuit requires linear depth. So, I mean, this is sort of discouraging because we have to cross linear depth. So you can ask this question whether can we do anything useful less than linear depth, but then you also will hit classical simulation limits, which is probably log n depth. So yeah, so it puts us in a weird situation where can we really solve or get some advantage using these methods? Because I think prior to, I mean, I think this was intuitive already, but prior to our paper, I think people were hoping that even though the cost value will get suppressed because of noise, but maybe we can still train and reach to the good solution. And after the quantum computation, after this running this variation algorithms, maybe we can classically get the true value, like noiseless value. But what we are showing is that even like you cannot train at all. And this is also, you can see in our numerics where we were studying the QA, and I think we focused on max cut problem with 5 nodes, so like 5 qubit circuits, and we generated like 100 random graphs. And then here we are plotting the gradient value of the cost function, and we chose the parameter as the middle parameter in the whole circuit. And here you can see that if it is noise free, if there is no noise, then it does not have any issue of vanishing gradients. But as soon as you add noise, then it just makes everything bad. Like your gradient goes exponentially down. Another thing which I should mention is that it's not just the gradient value. Obviously, the cost function value should also go to the fixed point, like the cost value corresponding to the fixed point of your noise. For example, in this case, we were studying Pauli noise. So the fixed point for that is maximum mixed state. But these plots were made actually for even general noise model. So we followed the IBM's device noise model. So even though our analytical results were specifically for Pauli noise, but these plots were made for like it also includes amplitude damping noise. So what should we do now? Like we should not go to linear depth circuits because we will not be able to train. So I think after our paper, we started asking if error mitigation can help with this. And I mean, recently 2 papers appeared which were studying whether error mitigation can help or not. My hunch is that we'll have to do some sort of error correction, even if it is not fully fledged, to even get something useful out of these algorithms. So I think with that, I will just conclude and just highlight the papers for both noiseless and noisy case. So I think you can divide these barren plateaus into mainly three different categories, but maybe, I mean, I think there could be more. So one is like randomness induced, which was McLean and co-authors, which they introduced first. And then Cerezo and co-authors, they introduced these cost dependent, where global has barren plateaus irrespective of any depth, but local has only when you go to poly and depth. And I should emphasize that whenever people talk about poly and depth and log and depth, those were like quite specific to hardware efficient onsets. Like they do not apply to QAA setting or HVA setting or UCC settings. And the reason is that, yeah, I mean, their proofs actually relied on the structure of the onsets. So these global and local cost functions should not be taken like directly for any onsets. It should be only taken for that specific like block structure onsets. And then entanglement induced barren plateaus, where Maria and co-authors like studied it for these block structure onsets, and also for Boltzmann machines, where they argued that if your unitaries are entangling unitaries, like highly entangling unitaries, then also you will have these issues. What we did in our other paper, we try to connect the expressiveness, but only through one way, which is if it is highly expressive, then you will have these issues. But then we don't know, like we don't have a concrete answer, but numeric suggests that sometimes, at least in the context of local cost, again, we were using these hardware efficient ansatses. That's why in the local cost setting, it really worked, that if you lose some expressiveness, then it becomes trainable. We also studied problem inspired ansatses, but they were specifically for these periodic structure ansatz, let's say QAA and HVA, but we did not study UCC. And I think our framework could provide maybe new strategies to develop adaptive ansatzes. Now you can ask, like, what are the ways? I mean, are there any ways to avoid or suppress the effect of barren plateaus? So problem-inspired ansatzes are one, but you cannot design them always. As I said, at least in the QML setting, it's highly unlikely that you can design problem-inspired ansatzes. And there was a recent paper from the Los Alamos group where they studied these variable structure ansatz, and just because variable structure ansatz like is always including some new gates or removing some gates, I think it just creates a cost function landscape, which is highly non-trivial. And I think, and it's also not like a fixed cost function landscape. So I think at least maybe if it is not like a problem where you require too many parameters, maybe variable structure ansatz can help. I should have included it here. Parameter correlation can help, and this is also related to like what we showed in our problem inspired ansatz paper. There are results which says that maybe pre-training or layer by layer training can remove, at least like improve these gradients, but I don't think they could completely avoid barren plateaus. But I think maybe more results are required in that direction as well. As I said, that QNNs, they are great examples of where because it's just log n depth, and it was also shown in this paper that they do not suffer from barren plateaus. So at least cases where you want to classify your quantum data, or let's say classical data encoded in quantum data, maybe QCNN, I mean, it's a good choice because they do not have these issues. And as Mario was asking question earlier, that all these results were mainly relying on these Hamiltonian expectation value cost functions. But if you change the cost function, then you can avoid barren plateaus. So what they studied in this paper was, Maria and co-authors, was if you replace your cost function, I think it was a QML setting where you are trying to learn a target state. And there they use the Zani divergence as a cost function. And I mean, they can avoid barren plateaus. So that's a good news. And I think we should study those kinds of cost function more. And in the noisy case, so there were two recent papers on error mitigation, if they can help for these algorithms. And I think answer is not obvious. And I think maybe it's sort of more negative because you can imagine that error mitigation can be thought of as a post-processing of your quantum data by, let's say, maybe taking more data and then doing post-processing. Whatever you do to improve your training, it more or less will affect the variance of your true value. So maybe you will improve, you will maybe, let's say, increase the value of your gradient, but also you're losing the certainty or accuracy, or I mean, in other words, like the variance of your actual value will go up. So that's again, like, I mean, this is, I think everyone believes that error mitigation alone will not help, and we'll have to do some sort of error correction. So there was this recent paper from IBM, where what they were suggesting was that, let's say, once we reach to a stage where we can do transversal gates, so we can do transversal gates, whatever transversal gates we can do error correction for them. And whenever we have to inject, let's say, magic states to apply T gates, there we can apply error mitigation. And at least maybe there we can use these algorithms effectively. And with that, I think, thank you so much for your patience and attending the talk.
Thank you, Kunal. That was a really great overview of what can and cannot be done with these variational NISQ algorithms. So we have one question from Chris, who is already leaving, but he promised to check the answer later from YouTube. So Chris's question is, which results are compatible to what is known or observed in classical deep learning?
I see. Yeah, I think maybe I cannot comment much on that, but so in classical deep learning as well, they had these band plateau issues, but as I said earlier, it was more or less connected to the depth of the circuit. But what new in quantum we have is that it is also connected to the width of the circuit, which means number of qubits. Because if you look at the global cost function, you don't even have to go to any depth. Even if you are at constant depth, you still face the band plateau issues. So, but I think, yeah. So your point was good, that if there are results studying the expressiveness and trainability issues. So yeah, I would be curious to check that out in classical literature. But I'm not sure if there are instances where they connect these problem-inspired things with trainability. Yeah, so I'm not sure about classical literature.
Do we have more questions? If not, maybe we can stop the recording and we can follow up with more informal discussion.
Mm-hmm.